All right. It's week 5 Friday. We are, I guess after today's lecture, we are halfway done with the quarter, which has both been, well, for me, it feels like a very long quarter, but also like I just feel like I'm losing track of time. So anyway, this is where we are. I appreciate everybody who responded to the kind of mid-quarter survey, and I empathize with everyone's unique situations, but it seems the general consensus is that we miss being on campus, we miss seeing real life people, and there's a lot more distractions at home. uh, this is not the ideal learning situation, but alas, this is kind of just where we are right now. So I take that into mind, and I think through all of that, and yeah. So anyway, thank you for your responses. That'll help inform the decisions that I make. Okay. Anyway, we will go on here, and our lecture is covering Fisher information, and we introduced this topic on Wednesday, but we didn't get that far into it. But the idea here is that if you look at a univariate function, the first and second derivatives, there's a lot you can learn about from the second derivative. Okay, so the first derivative is useful. That's the value of the slope. Okay, but then the second derivative tells you how quickly that slope changes, and it tells you about the curvature of the function. And then furthermore, the sign of the second derivative tells you about whether the function is concave up or concave down, and whether x is a local min or local max. Okay, and so that's what we got on univariate derivatives. And then what we're going to look at today is going to be the kind of the multivariate case. Eventually, we'll get there. And so the gradient of some kind of function with respect to w is going to be a vector consisting of all of the partial derivatives with respect to each component in w. Okay, so so the gradient of f with w is going to be this vector of all of these partial derivatives. You can kind of think of this as kind of the multivariate generalization of a derivative. And then if we ask for the second derivative, okay, the second derivative with respect to a vector, okay, then you are going to get a Hessian matrix. Okay, you're going to get the Hessian matrix, which is going to be f with respect to kind of each column here. And so, if we kind of look at this a little bit closely, the gradient of f with respect to w is a vector. Each component is a partial derivative. And if you take each partial derivative and you take, what's the gradient of that with respect to w to kind of get the second order partial derivatives here, then, this would become a vector. Okay, this is the vector of basically kind of like the gradient of this, the vector of partial derivatives. And therefore, you can think of the Hessian, okay, which is basically the matrix, the matrix derivative of a vector. You can think of this also as the Jacobian matrix of the gradient vector. Okay, so so you get the gradient vector. You can think of the Hessian as also equivalent to the Jacobian matrix of the gradient vector. So I don't know if you guys remember all of these matrix linear algebra terms and stuff, but this is what we've got here. Okay, so the when we had the univariate first and second derivatives, we said the sign of those derivatives of the second derivative told us about the concavity. And similarly, when we have the Hessian matrix, we have we can look at the definiteness of the matrix, okay? And so if it is positive definite, okay, then all eigenvalues in the matrix are greater than 0, and the function is going to be concave up, and the value at x is a local min, okay? So, you know, if the gradient of a function is 0 at some point x, then we can look at the Hessian matrix. If the Hessian matrix is negative definite, then the function is concave down, and then x is going to be a local max, right? And then if you have a mix of both positive and negative eigenvalues, then it's neither positive nor negative definite, and you're going to have a saddle point at the point x, okay? And then if it's, you know, positive semi-definite or negative semi-definite, meaning some of the eigenvalues are equal to 0, you're going to need more information to determine concavity of the function. All right, so there's you can read up on the Hessian matrix on Wikipedia. The Hessian matrix is symmetric, okay, because you know, if the second derivatives are continuous, then the order of differentiation doesn't matter. So back here, you know, the second derivative with respect to W1, then W2 is going to be equal to the second derivative with respect to W2 and then W1. Sorry, give me a second here. And so, like so the second derivative of a univariate function told us about the curvature of the univariate function, and similarly, the Hessian matrix of a multivariate function tells us about the curvature of this multivariate function. Okay, when you apply the Hessian matrix to the likelihood or the log likelihood function, okay, the curvature can tell you how confident you can be in your parameter estimates. Okay, so learning about the curvature of a function will can also inform you about how confident you can be in your parameter estimates. So, I'm going to start us off with a univariate example, okay? And we're going to look at the second derivatives of a univariate function, and we're going to see how the second derivative of a univariate function tells us about how confident or how much information we have about the parameter estimates. And then we're going to generalize it to the multivariate case. Okay, so here I've got, I don't know, just a silly example here, but let's pretend I've got this pouch here, and let's pretend that there's some marbles in here, okay? In this marble in the pouch I've got red marbles and blue marbles, and we don't know what proportion in the pouch is red, okay? There's some value, okay, some proportion theta, but it's a mystery value to us, okay? And so we're going to try to learn what that proportion is by observing data. So I'm going to reach into the pouch, pull a marble out, look at it, and then I'm going to put it back in the pouch, okay? So and then I shake it up, and then I reach in there again, pull a marble out, I put it back, shake it back up, okay? And we're going to do this 10 times. We got 10 marbles. We're going to draw 10 marbles with replacement, okay? And let's say we've observed 4 red marbles, okay? So in this case, for our data, the likelihood of our data is going to be theta raised to the 4th and 1 minus theta raised to the 6th, okay? This would be the likelihood of some exact sequence, say red, 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 followed by blue, 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 okay? That would be kind of the probability or the likelihood of some exact sequence. if we were said this was a binomial problem and we wanted a binomial probability, then there would be a, you know, a binomial coefficient factor in the front, you know, 10 choose 4 and things like that. But this is not a probability per se. It's not a probability function. So there's no requirement that this has to sum to 1 across different values or anything like that. Okay, so here I've just got some function of theta, okay, and we want to say what is the likelihood of our data for different values of theta here, okay? And so I'm going to graph this, and we're going to see, you know, what is the likelihood of this outcome of getting four red marbles across different values of theta, okay? And so our likelihood function looks like this, okay? Remember, this is a function of theta, saying that if the proportion in our pouch is 100% red, okay, the proportion is 1.0 for red, then the likelihood of drawing 4 red and 6 blue is 0, okay? Okay, or it would be impossible for me to get 4 red and 6 blue if the pouch is 100% red, okay? Similarly, if I'm down at 0, okay, the probability of me getting, or the likelihood of me getting 4 red and 6 blue is going to be 0 if the proportion in here is 0 red, okay? If theta is 60% red, okay, 0.6 red, then my likelihood is somewhere around here, meaning that if this is 60% red, then yeah, sure, I can draw 10 marbles and only get 4 of them to be red, okay? The likelihood is maximized when theta is 0.4. If the proportion inside this pouch is 40% red, then I have a very high likelihood. The likelihood is the highest if I assume that this is 40% red, okay? Because I drew 10 marbles, 4 of them were red. It kind of makes intuitive sense that that's the going to be the highest, have the highest likelihood, okay? But you know, values like if somebody said, you know, the proportion in here is 30% red, we would believe it, okay? 30% red, that makes sense, okay? That's not unbelievable. If someone said it's actually 50% red and you just happen to only get 4 red out of 10, that would also seem very, very believable, okay? So there's going to be high likelihoods for values like 0.3, 0.4, 0.5, and everything in between. And even values like 0.6 or 0.7 are not completely eliminated, right? Those are not completely, like, if you told me that the pouch is 70% red, we'd say, oh wow, we got kind of a unique circumstance where only 40, you know, only 4 out of the 10 draws were red. I would have expected to get a few more, but it's also not completely impossible, okay? And it's really only until you start saying that the pouch is 90% red, where it becomes almost impossible for us to get 4 red out of 10 draws, okay? So that's what this slide sums up. It just basically says that the 0.4 is the maximum likelihood, and you have other values like 0.5 or 0.3 that also have high likelihoods. Okay, so let's pretend I continue this thing where I've got the pouch, and you know, I shake it up, I draw a marble, look at it, and I put it back. Let's say I do this 1,000 times. Okay, I draw 1,000 marbles with replacement, and let's say I observed 400 red marbles this time. So I observed 400 red marbles out of 1,000, and in that case, your likelihood is for, you know, some exact sequence, okay, is going to be theta raised to the 400 times 1 minus theta raised to the 600. Okay? So what does the likelihood function look like here? Okay. If you graph this across different values of theta, this is what it looks like. Okay. We have a sharp peak at 0.4. Okay. And then pretty much everywhere else, it's pretty much 0. okay? So if it were 100% red, it would be impossible, practically impossible for me to do 1,000 draws where 400 are red and 600 are blue, okay? Even values where if it was 0.5 red, okay? So if you told me that the pouch is 50% red, okay? If the pouch were 50% red, then it's almost impossible for me to do 1,000 draws and only get 400 red, okay? If it was 50% red, if I do 1,000 draws, then I should get something very close to something a lot closer to 500 red. And the fact that I only got 400 red is practically impossible, okay? And only values near 0.4 are going to have high likelihoods, okay? So if you told me that the pouch is 41% red, yeah, I could believe that. You know, if it was 41% red, sure, after 1,000 draws, I might only get 40% red. I might only get 400 red, okay? Or if you told me that the pouch is 38% red, you know, I could believe that after 1,000 draws, I happen to get 400 red. But, you know, anything lower than, say, like 35% or higher than 45% suddenly becomes, you know, almost impossible. You know, if you say the pouch is only 35% red, then how do you explain that I got 400 red? Okay, the likelihood of getting 400 red if the pouch has a true probability of 35%, that likelihood is very low. Okay, because I'm getting, you know, a lot more red than I should be getting. So with so in both cases, okay, in both cases the observed proportion of red is 0.4, and the maximum likelihood is the likelihood is maximized when theta is 0.4. 4 out of 10, theta is maximized at 0.4. 400 out of 1,000, theta is maximized at 0.4. But what we see is that over here, with only 10 observations total, a lot of other values are highly likely, okay? 0.2, 0.3, 0.4, 0.5, 0.6, you know, and everything in between, because there's nothing that says it has to be, you know, you know, you got good continuous values of theta. This this is what it looks like, okay? And so, whereas over here, only there's a much tighter band of kind of plausible or believable values for what theta could be. Okay, so so we're going to say that you know, values like 0.39 and 0.41 have high likelihoods, but there's pretty much zero likelihood for theta being 0.3 or 0.5. Okay, and we would say that there's much less variance as far as what theta could be, and this is related. This is related to basically how confident we can be in our estimates. Okay, in this case, if our maximum likelihood estimate is 0.4, and I'm very confident that theta is something close to 0.4. Over here, my maximum likelihood estimate is also 0.4, but I'm a lot less confident that theta is very close to 0.4. Okay, there's a lot more spread or uncertainty in what theta could actually be. Okay, so let's tie this back to the second derivative, right? The second derivative measures the curvature of the function. All right, so the likelihood of 10 draws and 4 red, that's theta to the 4, 1 minus theta to the 6, okay? And if I take the log likelihood, okay, the log of this likelihood function is going to be 4 log theta plus 6 log 1 minus theta, okay? And I take the derivative of that, and I get 4 over theta plus 6 over 1 minus theta. And I take the second derivative, so the derivative of this, okay, this is basically 4 times theta to the negative 1. So that becomes negative 4 theta to the negative 2. Okay, so negative 4 over theta squared. Same thing over here, I get negative 6 times 1 minus theta squared. Okay, and you know what? I'm missing a negative sign here. did this wrong. Okay, sorry, this should be a negative sign, I think. All right, and then if I do the same thing with theta to the 400 and 1 minus theta to the 600, this would be the likelihood function of 1,000 draws, 400 red, 600 blue. We're going to get this, okay? And this thing is pretty much equal to 100 times this, right? So this is the second derivative of the log likelihood. This is the second derivative of the log likelihood. So we can get the observed information, or we can just plug in, you know, what is the, let's plug in our maximum likelihood estimate and get our value. So the second derivative of the log likelihood at our maximum likelihood estimate is 41.67. And when I do it for the 1,000 draws, the likelihood for 1,000 draws, then the using the maximum likelihood estimate, I get something like negative 4,167. Okay, so you know, the second derivative measures the curvature of the function, and this tells us that you know, what we already know, that the likelihood function has a lot more curvature when you have 1,000 draws. Okay, and so again, looking at this, from here, the slope is positive, okay? The slope is positive, and then it slowly changes. It gets less and less positive, and then it becomes negative over here, okay? And then, you know, how far negative does the slope become? You know, I don't know what negative slope this is. It's not dramatically negative, okay? Whereas over here, if you look at the slope, it goes from very positive, okay, right over here, from very positive to very negative very rapidly, okay? So we go from very positive, very steep upward slope, and then it rapidly changes to very negative right over here, okay? So in this small span, it goes from very positive to very negative, whereas over here, we're going from kind of positive to kind of negative, okay? So the curvature is a lot lower. And that's just what the second derivative measures, okay? All right, and so, you know, the idea that the slope changes rapidly tells us that the kind of the data that we have provides a lot more information about the location of theta. And specifically with 1,000 draws, we have 100 times more information about what theta should be than what we did after only 10 draws, okay? And so the relationship between the curvature of the likelihood function and the information we have can be tied together in what we call the Fisher information. And so I know you guys learned, or at least you know, should have learned a little bit about Fisher information in your 100B class. You know, there's different definitions or different ideas for what Fisher information can be, okay? But here we're going to take it as a way of measuring the information that a random variable can provide about some unknown parameter, okay? So the formal definition of Fisher information is that it is the variance of the score, where the score is the derivative or gradient of the log likelihood, okay? So it's technically the variance of this quantity, okay? What's the variance of this quantity? But if the log likelihood is twice differentiable, then the Fisher information is also equal to the negative of the expected value of the second derivative of the log likelihood. That's like a whole mouthful here, okay? But and Fisher information can be used to kind of prove the lower bound of the, you know, Cramer-Rao bound and stuff. But here we're going to use it as telling us about how much information we have about some unknown parameter theta, okay? Do we have a lot of information about it, or do we have less information, okay? So the way it works is that we've got some function, okay, some function, some probability function. This is either a PDF or a PMF, probability function of a random variable x. The random variable x, this PDF is defined by parameters theta, okay? So, so if your PDF's the normal, then, theta would be kind of your mean and variance. If x is Bernoulli, then theta is your probability value and stuff, okay? And what we said is that the Fisher information is equal to the negative of the expected value of the second derivative of the log likelihood, okay? So first we're going to talk about the second derivative of the log likelihood, okay? That's what goes inside here. We've got the log likelihood function, and here is the second derivative of the log likelihood function, okay? All right, so we've got the second derivative of the log likelihood, and then the Fisher information is negative of the expected value, okay? All we're doing is negative of the expected value. All right, so these two things are exactly the same. It's just important to remember that the expected value is taken with respect to the random variable whose distribution is defined by this function f of x, f of x given some parameter value theta, okay? So it's the expectation of the random variable, okay? So for the other lecture, just kind of a quick review of what your expected values are, right? So the expected value of y, okay, this is the notation is that I'm just putting in a reminder of what the PDF of y is, okay? PDF or PMF of y is. So this is the probability function of y. And so you can just say the expected value of y is the expected value of y where, y has this probability function, f of y, and this is equal to the integral of y times f of y dy, right? So the expected values, you take each possible outcome y, you multiply it by the function y, the probability function y, and you integrate across all possible values y, okay? So it's the integral of y, f of y dy, okay? Or if y is discrete, then you're going to take each outcome y, multiply it by the probability of y, and then you sum them up, okay? So that's going to be the expected value of y itself. You can also take the expected value of some function of y, all right? So if you have some function of y, g of y, okay? Again, the random variable y has the PDF f of y, okay? The random variable y has the PDF or PMF f of y. And so the expected value of some function of y, g of y per se, is going to be the integral of, and you take each value, g of y, and you multiply it by the probability of getting that value, f of y, okay? And you take the product of those things and you integrate it across all possible values of y, okay? Or if y is discrete, then it's the sum rather than the integral. So you take every possible value of y, every outcome y, you plug it into your function g of y, and then you multiply it by the probability f of y, right? So the expected value of y is this. Your variance is going to be the expected value of basically y minus, basically mu of y, the expected value of y quantity squared and things like that. So so that's what we. So the Fisher information is going to be the negative expected value of the second derivative of the log likelihood function. Okay, I want to pause there and just kind of make sure everybody's doing okay and following along. If so, give me a green check. If not, give me some other indicator on Zoom. And let me also give you the first quiz question. First quiz question is D as in dog. D as in dog is your first quiz question. Okay. Okay, so so this is what we have here. All right, so what I'm going to do is we are going to find the Fisher information for the Bernoulli experiment, okay? So again, we're still in our univariate case, okay? And so for the kind of this Bernoulli thing, for one observation, let's just do it for one observation, okay? So we want the negative expected value of the second derivative of the log likelihood function, okay? So our likelihood function for one observation is just the PDF or PMF. And so I've got theta to the x, 1 minus theta to the 1 minus x. And it's the log of that. So if I take the log, I got log theta x plus, so the second derivative of log 1 minus theta 1 minus x. The log is x log theta, and so on and so forth. The derivative of, second derivative of x log theta will be the derivative of this. So the derivative of x log theta is x over theta. And the derivative of this is going to be 1 minus x divided by 1 minus theta. And the second derivative, okay, the derivative of x over theta is going to be negative x over theta squared, okay? And over here, the derivative of this is going to be 1 minus x over 1 minus theta squared, negative of that, okay? And so the Fisher information is going to be the expected value, the negative expected value of this whole quantity. So I can take, the expected value of a sum of random variables is the sum of the expected values. So I've got the expected value of x over theta squared plus the expected value of 1 minus x over 1 minus theta squared, okay? And and so for our Bernoulli random variable, the expected value of x is equal to theta. The expected value of x is equal to theta. So, so what I've got, this is where I left off. The expected value of x is theta. The expected value of 1 minus x is going to become 1 minus theta. And that simplifies to 1 over theta plus 1 over 1 minus theta. And then if I find the common denominator and I add these together, the Fisher information is going to be 1 over theta times 1 minus theta. Okay, that's the negative expected value of the second derivative of the log likelihood function. All right, so that's it's quite a mouthful, but that's what we have. Okay, so that's the Fisher information. All right, I hope that's okay. And then a nice property is that Fisher information is additive. Okay, so each observation of x gives us this much information about the unknown parameter theta. Okay, so each observation we have gives us 1 over theta times 1 minus theta. And so if I have n observations, if I get 10 observations, then I've got then I'm going to have n times that. Okay. And if I have 1,000 observations, I'm going to get 1,000 times that. All right. And so, so when we had 1,000 observations, our Fisher information was, 100 times bigger than when we only had, 1 observation, 10 observations and stuff. Okay. So that's Fisher information for our our Bernoulli experiment with just kind of one outcome and one parameter. So what we're going to do now is we're going to generalize this to the multivariate case. Okay, and so the second derivative told us how confident we can be in our parameter estimates, and basically, what we saw for the Bernoulli case was that the more observations you had, the more confident you can be in your estimate of theta. Okay. And what we want to do is we want to generalize this to the multivariate setting, okay? And so the second derivative in the multivariate setting would be the Hessian matrix. And so the Fisher information, which we're going to say again, if the log likelihood is twice differentiable, then the Fisher information is the negative expected value, this time of the matrix of second derivatives, okay? So of the log likelihood, right? So we're going to take the second derivative of the log likelihood function, and we're going to ask for the negative expected value, okay? And again, I have it with this subscript to indicate that we're taking the expected value with respect to our random variable x. And we have the log likelihood function of x, and we're going for the second derivative. The derivatives are taken with respect to the unknown parameter theta, okay? So we're taking derivatives with respect to the unknown parameter theta, and we're taking the expectation with respect to the random variable x, okay? So it's important that we kind of keep track of, what we're doing with respect to which variables. Okay, so this is, I think this translates kind of easily, right? So if we have a univariate function, it's just the second derivative of the univariate function. And here for a multivariate function, it's going to be kind of the second derivative with respect to kind of your multivariate vectors. So you're going to get a Hessian matrix. All right, let's do this for linear regression, okay? So in linear regression, we're going to do it for the coefficients W, okay? We want to say, what information do our observations provide about the unknown coefficients W, right? So we're in linear regression, we try to estimate, what your slope and intercept and your other coefficients are based on your input variables x and the outcome variable, in our case, t, okay? So the outcome variable is t, and if we assume that the errors are normally distributed, then the probability function of each observation is going to be the normal PDF, right? The normal distribution, where the mean is W transpose X of n, okay? So the mean is going to be basically the product of your weights and your input vector X. And we're saying the values that we observed are normally distributed around kind of that mean function value with variance sigma squared, okay? So that's kind of how we set up our generative model. We're saying the observed values of t come from the normal distribution. So that the probability function of the outcome variable t, okay, it's a function, it's the normal PDF, and these values, w, x, and sigma squared, are basically parameters of this function, okay? And we treat x, the input variables x, as far as the likelihood function goes, x is are fixed values. So is the variance. Sigma squared is also fixed values. Okay, we're treating these as fixed values, and w is the unknown parameter that we are trying to estimate. Okay, it's the coefficients w are the unknown parameter that we're trying to estimate. And so we want to know what is the information that we have about the unknown parameter w. Okay, what's the information about w? Okay, is going to be the negative expectation of the second derivative of the log likelihood function. Okay, so so here the likelihood function is going to be the product of all the normal PDFs, right? So the likelihood function of your total data set is going to be the product of all the normal PDFs, and we want the log likelihood. Okay, so we've got the log likelihood. We want the second derivative of the log likelihood, which is going to be this quantity here. Okay, second derivative of the log likelihood. This here is the Hessian matrix of the log likelihood. This matrix here. And we want the negative expected value of this. What's the negative expected value? And remember, we're taking it with respect to the outcome variable t. Okay, each t sub n is, comes from here, and we're not taking it. We're often accustomed to saying, what's the expected value, and x is our random variable. But for linear regression, in our generative model, the input values x are fixed values, okay? and only the outcome variable t, these are your observed actual values, those come from a probability function. So it's going to be the expected value with respect to this outcome variable t, not with respect to x or sigma squared. Okay, and so this is, we're going to take this part, the likelihood. Okay, I'm going to expand that out. I'm going to expand out the likelihood and the log likelihood. So this is the part I work on in this slide. And we saw this already in lecture 5.1 earlier this week. And so, so this is what we have. The likelihood function is, this is the normal PDF, okay? So again, it's, t is our random variable. The mean for each observation t is going to be w transpose x sub n, and then sigma squared is also fixed values. So these are fixed values. This is a fixed value, and then our random variable is t sub n. So this is our likelihood function. It's the product of all of our normal PDFs. And the log likelihood, okay, is going to turn the product into a sum, okay, and I have to apply the log to all of this. And if I expand that out, okay, all of these things are constants with respect to n, and so this becomes negative, you know, all of this. Okay, so this is the log likelihood that after we expand it out. Okay, and so here's my log likelihood, and now what I want to do is I want to take the derivative of this, and I did all of the steps in lecture 5.1. Okay, and so you know, just quickly going through, this becomes, you know, when you expand all of this out, you get x transpose t minus x transpose x w, okay, and the log likelihood times 1 over sigma squared. Okay, we're taking the derivative with respect to w, okay, and so, you know, the gradient is going to have the same dimensions as w, and that's going to give us a k by 1 vector here. Okay, so here I've got a k by 1 vector, and I want to take, I've got the derivative of this, all right, and that's going to give me this. Okay, and so now I want to take the second derivative. Okay, so the second derivative, so basically I'm taking the gradient of this thing. I distribute the 1 over sigma squared, so I got 1 over sigma squared x transpose t minus 1 over sigma squared x transpose xw, and I'm going to take the basically the Jacobian of this thing, because this thing is a vector. So this thing's a vector, and I want to take the derivative of that. So I want the Jacobian matrix of this vector, okay, or the Hessian matrix of the log likelihood, the original log likelihood value. And so when we do that, then I'm going to get a k by k matrix, okay. With respect to w, we take the gradients and the Jacobians with respect to w. This is going to be a constant. This is going to drop out to 0. And over here, this thing, there's a w here, and so with respect to w, it's going to be negative 1 over sigma squared x transpose x. So this is the Hessian matrix of the log likelihood, the Jacobian matrix of the gradient vector, okay? And that's going to be 1 over sigma squared x transpose x. All right. Is that all right? Do we feel okay with what we got here? Let me know if you're not following along, or if anything, if you got lost along the way. Let me give you the second quiz answer. Second quiz answer for today's quiz is C. C as in cat. C as in cat for the second quiz answer. All right, so this is the Hessian matrix of the log likelihood. Okay, it's going to be 1 over sigma squared x transpose x. Okay, and so the last thing that we're going to do, all right, is the Fisher information is negative, the negative expected value. Okay, negative expected value. All right, and this is where it feels a little bit weird, but remember, x in our in our example, x's are fixed values, okay? They are constants, okay? Because we are taking the expected value with respect to our outcome variable t. T is coming from the normal distribution where the mean is W transpose X sigma squared. So Portent is asking, is the Hessian of the log likelihood the same as the Jacobian of the gradient? So it's the Hessian is equivalent to the Jacobian of the gradient. The Hessian of the log likelihood would be the Jacobian of the gradient of the log likelihood. Okay, so you need the gradient of the log likelihood, and you take the Jacobian of the gradient of the log likelihood. That would be the Hessian of the log likelihood. I'm pretty sure. The Hessian matrix of a function f is the Jacobian matrix of the gradient of the function. Yeah. Okay, so the Hessian of the function f, so in this case, the Hessian of the log likelihood will be the Jacobian of the gradient of the log likelihood. Yeah. Okay, so the Fisher information is equal to the negative expected value of the Hessian matrix of the log likelihood. Okay, so here the Hessian is this. All right, so remember, we're taking the expected value with respect to the outcome variable t. Okay, and with respect to the outcome variable t, this is just a constant. Okay, so the negative expectation of this constant is just going to be 1 over sigma squared x transpose x. Okay, and this is the information that our data provides about the unknown parameters w. Okay, so what do we, the unknown coefficients w, what information do we have about that? Is going to be 1 over sigma squared x transpose x. Okay, and again, remember the Hessian matrix measures curvature. So if you got, if your log likelihood function is smooth, is not super pointy or anything, has low curvature, then you're you don't have as much information about the parameters. But if you've got a lot of information, then what you're going to observe is that your I guess it's technically it's concave up. So if you have a lot of information, a lot of observations, then your the function is going to be very sharp. Okay, so you can imagine a three-dimensional bowl that's very, very sharp, high curvature, very quote unquote pointy. Okay, whereas if you have very few observations, then it's more of a shallow bowl where there's a lot less curvature. It's a little bit more flat. Okay. So anyway, all this to say is that also the other part is the amount of noise. Sigma squared in our model is the variance of this epsilon value, right? So W represents the true values, and then you've added some noise into this to get the observed values T. Okay, if there's lots of noise in this epsilon, then sigma squared is going to be large. Okay, sigma squared appears in the denominator. So if sigma squared is large, the Fisher information is small, and you have less confidence in your estimates of W. If there's little noise, sigma squared is small, the Fisher information is large. What did I say? Yeah. So sigma squared is small, Fisher information is high, and you have more confidence in your estimates of W. Okay, which makes sense, right? So if there's lots of noise, there's going to be lots of scatter, and you're going to have less confidence as far as what if your slope and intercept parameters are close to the true values. On the other hand, if you have very little scatter, then you're going to have a lot more confidence that you've got the kind of correct slope and intercept parameters there. Okay, so Fisher information, I know like the definition, right? The negative expected value of the Hessian matrix. It's like too many pieces for your head to get wrap around. it's actually negative expectation of the Hessian matrix of the log likelihood, right? Like that's so many things. Okay, the important thing is that the second derivative measures curvature, and basically as you have more curvature, then that means you have more information about what the unknown parameters are. If you have less curvature and it's a lot more shallow, you have less information about what the unknown parameters are. Okay, that's all I've got for you guys today. So that will end our lecture. I hope you guys are doing well, and we will see you guys on Monday. So welcome to the month of May. Happy Friday, you guys.